Hello everyone, welcome to all in this lecture. So today I'm going to discuss design of shallow foundation, or in this lecture I'm going to discuss the special topic, that is design of concentric loaded split footing. In the previous lecture I have discussed about the design of a strip footing. So in this lecture I'm going to discuss the design of shallow foundation and design of concentric loaded split footing. So we have seen that shallow foundation, basically we know that when the depth of foundation is less than equal to width of foundation, so that is called a shallow foundation. So there are different types of shallow foundation. So in the first lecture I have discussed about the strip footing. So in this lecture I'm going to discuss split footing or isolated footing. So we are going to design a concentric load split footing. Split footing, basically that footing we design for the support individual column, right? Okay, and the shape of a split footing can be circular, can be rectangular, and can be a different shape like slope and step, like a step. It can be a step. Okay, leave it. So in this, you can see I have mentioned here the concentric load. Concentric load. What is the meaning of this? Concentric load, we will call, say, two types of load will come on the column. First, suppose that concentric, it means the line of action of load. Suppose this load Q is coming on this column, and this is the, suppose, a footing. So this will coincide the CG of column. So if the load will coincide the CG of column, so we can call a concentric loaded split footing. And suppose this Q is not coincide with the CG, it is somewhere else, like here, Q is coming here. So you will get some eccentricity, and this load is, we can call eccentric load. So you will get, in this case, there is extra moment will come Q into E, right? And due to this moment, what will happen? The pressure will develop at the base will be not uniform. Not uniform. One side you will see there is a minimum, and one side you will see there is a maximum. Okay, but in this case you will see there is a uniform pressure. There is a uniform pressure at the base. So we can go for design a square isolated footing. In this case, when uniform. But for this case, maybe we have to go for the trapezoidal footing. Maybe we have to go for the rectangular footing. So it is very important to it is very important to be sure about the load is coming concentric or eccentric, right? So we will see both the cases when the how will we design isolated footing with the concentric load are coming. How will we can design the isolated footing when eccentric load are coming due to some with some eccentricity, right? So in this lecture I will discuss and I will design isolated footing when the concentric load are coming. In the next lecture I will discuss eccentric loaded split footing. Okay, so let's see. So in this slides you can see I've mentioned some figures. So there are different types of isolated footing, isolated footing. So in the first case you can see there is it is called single footing, or you can say single. You can also call single step footing. So you can see there is a Q coming on the column, and there is a. Why we need to provide footing? So we have to distribute all this load over the larger area, so that the whatever the pressure will develop at the base, we have to be keep less than equal to QNA, where the QNA is soil allowable pressure. Soil allowable pressure. So generally what we do, we keep this value in leisure. Don't go for equality sign. We just provide this to be safer side, right? So it depends upon the what is the amount of load that coming on the column, and it can be get satisfied or not. So accordingly we design like this. In the second case, you will see there is a stepped isolated footing. So in this case, when the large load are coming on the column, so we go for the larger area to support this. So what we do, we don't go directly to the larger area. We first increase this area up to, suppose this is the A1. Okay, next we go for again larger area, that is a A2. Again we can go for A3. So you can see we have to be distributed this load to A3, but we directly we are not going directly to A3. We just first we have design A1, then load are coming on the A2, means this Q load are distributed over the A1 area, then pressure is distributed on the A2, then A3. So it's coming like that. In the large area, large load are coming on the column, so we have to design like this. Okay, so what is the benefit of this? You will say in this next slide. So when punching shear will come, so it will avoid the punching shear. It will avoid the punching shear. Where the large load is coming, there is a chance to be punching shear. Two-way shear is called. Okay, so that's why we go for this design. The next one, that is third one, you can see. So here the load are coming. Suppose Q load are coming on the column. So here what we do, here you can see the load are first distributed over this area, then distributed over this area, right? But here it is a distributing footing are provided at a slope, right? You can see there is a slope, and this sloping you can design. So what will angle you can keep, right? What will be this angle? So this is called the slope isolated footing. Okay, so now we will discuss how to design. So this also isolated footing will design in a two-way. We can design as a plain concrete footing, and we can design also reinforced concrete footing. So whenever the load are laced and bearing capacity of soil is we have enough bearing capacity of soil that will resist that load are coming. So due to on the condition what problem we are getting, so we can design the foundation isolated footing as a plain concrete footing. So design of plain concrete footing are very similar to a split concrete footing that we have also seen in the previous lecture. So general some criteria we keep. So generally the thickness of cavity is twice the projection. So means what is the projection? So this is the footing. Okay, so this is the projection, suppose, and we design two-way. So thickness we kept equal to twice of the projection, right? So some basic procedure that we have to follow. Always we have to follow this procedure, and this is same for any kind of foundation. Like suppose you are going to design any foundation like strip footing, like isolated footing, combined footing, or any other footing. So you have to follow all this procedure, right? So first, but we have to suppose A. So whatever the load coming on the column, we have to design for this. So we have the Q, and we have this QNA by performing some test like bearing capacity shall be found, and then you apply some factor of safety. Then we got QNA. So before going to design a footing, we have to know what is a QNA. Okay, and load are coming, so we know both the things, right? So we can calculate what area required. So according to that QNA, what area are required. So first we will calculate what area required. So suppose we got some required area, right? So what we do generally, we provide some extra area, some greater area compared to the required area to be safer side, right? So in that case, when we will increase this provided area, so again we have to calculate what is the actual pressure will develop at the base of the footing. Means we have to be go for to calculate Q naught. Or you will see in this case when the provided area is greater than required area, so we will see there is a Q naught less than QNA, right? To be safe side, if in suppose in case you have provided the same area as you have required, so you will see in that case that QNA will be equal to QNA. So no need to calculate the actual pressure. So generally, we always provide some greater area as compared to the required area. So we have to be go for the calculation of actual pressure that will develop at the base of the footing, right? So this procedure is common. Design of foundation or design of concrete and steel, anywhere you will see there is a procedure to design, and you have to follow what is the procedure, and you have to be you have to understand each and everything. So why we are doing the procedure, this procedure, what we are getting by doing this procedure. So you have to be very careful about that. So now we can go for next. Okay, the second one, that is reinforced concrete footing. So reinforced concrete footing we design when the bearing capacity of soil is not enough, or suppose the load are coming, that is higher load. So you will see that due to the higher load or due to the higher pressure will develop at the base, so that the structure, whatever we are designing for the concrete, it will not resist maximum bending moment that it will develop at the face of the footing, and diagonal shear and punching shear. So we have to be provided reinforcement, and you will see in this case, suppose this is this will okay, so this will act as a cantilever, actually cantilever. So you will see when the pressure will come at the base of the footing, that is Q naught, so it will try to bend in upper direction. So tension will develop here. So tension will be developed at the bottom portion, at the bottom portion. So we will provide reinforcement at the bottom side, right? In the left side also we provide a bottom side. This will also try to will go up. So whenever the we know already that concrete is weak in tension. So whenever the tension are coming in the concrete, so there at that place we provided, and we reinforce some bar, some steel bar, so that will take the tension, so that concrete will not fail. So that is called the reinforcement concrete. Okay. So now reinforcement concrete footing. So the basic procedure we have to always follow. Again, we have to find the required area that we can get by Q divided by QNA, where Q is the column load, whatever the load coming on the column, and QNA, soil allowable pressure, that we have designed, that we have calculated during performing some test on the field. So if the we have provided some extra area compared to the required area, some greater area. So always we have to be calculate to actual area. So we can calculate actual area by Q divided by actual area or provided area, right? So now we know that some critical section, so that we know for the bending moment there is a critical section at the face of the wall. So we have to be calculate the bending moment at the face of wall, right? So you can see in the figure there is a column and there is a width of footing, you can see, and there is a uniformly distributed in the strip footing. We have seen that there is a Q naught, but there also there was Q naught into 1. We have working for 1 unit of length, right? So here you can see there is a Q naught is the pressure, pressure. So how it will come? You will see this diagram. This diagram is like this. B and B. So we are here, right? We are here. So we are in this front. So this is the Q pressure developed everywhere. So what pressure will come at a UDL in this section? So we have to multiply with this length. So Q naught in the B. So that will be the UDL we have written here. Suppose this is the case of rectangular footing. Suppose this is the rectangular footing. Here in the this question, I mentioned the square footing. So suppose this is the case where the rectangular footing. So this side is B, this side is L, right? And this is Q naught pressure is developed. So what will be the UDL? So what will the UDL we will be? I'm saying Q naught into L, whatever the length perpendicular to this figure, perpendicular to this plane. So we can write Q naught. What is the length perpendicular to this direction? That is L. So we know we can write Q naught into L. I'll get to a point. But in the case of a square, there is a both dimensions are same, length and width. So Q naught into B, but you have to understand this B we have written that is perpendicular to this plane, perpendicular to this figure. So now we are very clear about how we can write UDL. So UDL we have. Okay. So at the face, you will see at the face of the column we have to be calculate. So width, there is a width of column, there is a small b, and we have to be calculate bending moment at a critical axis, that is critical axis for face of the column. So on the x-axis, so we have to be calculate the bending moment on x-axis. So you can calculate the dimension from the edge. So that is capital B minus a small b divided by 2. So how we can write bending moment? So to calculate bending moment at a x-axis, we have to be write what is UDL, then what is the length of the UDL, that is B minus B divided by 2 into what is the centroid of, what is the CG of that UDL load from the section. Section is XX. So at the section you will see that is small b divided by 4. So that is distance. See, centroid will come from here. So here to here, distance will be b minus b divided by 4. So that I have written here and here also. This is the length of UDL, and that is b minus b divided by 2. I have written here and I have written here also, right? And this is the UDL. This is the UDL. You can see I have written here also. This is the UDL. So now we are clear about how we can calculate bending moment at the x-axis. So after simplifying, you can get this result. You can get this result. After simplifying, you can get this result. So now for the diagonal shear, critical section is taken d distance from the face of wall, So how d distance are coming? Why we are taking on the d distance? You will see. So cracking is generally developed. You will see this is the. Okay. So you will see. Suppose this is the footing, and this is the column. This is column, this is footing. Okay. So we'll see crack generally develop from this point. So like this, and this angle is 45 degree here also. So this angle is 45 degree from here. You will see there is a reinforcement. There is a diameter of steel bar steel bar. Here the steel bar provided. This distance is D. This distance is D. So you will see there is a cracking pattern. So this will D. So D. So this distance is D. So angle is 45. So this distance also will be D. So that's why we take critical section for the diagonal shear at a x1, x1 axis. Suppose this x1, that is D distance from face of the wall or face of the column, right? So this is always remember why we are taking D distance from the face of the wall. So I think we are very clear about so why we are taking D distance from the face of the wall or face of the column, right? So now we can go for the calculation. So the x1 axis I have mentioned in this figure, you can see, and the distance from the edge, we can write B, capital B minus a small b divided by 2 minus D, where the D is the effective depth, capital B is the width of isolated footing, square isolated footing, a small b is the width of column, right? But you have to see and what edge you are working. Suppose in the rectangular column also there. In this case, there is a footing which is also a square and there is a column which is also a square in shape. But it can be rectangular. So rectangular dimension will be changed. So b into maybe length will come small l. So we have to be see. In the next lecture, I will discuss the rectangular footing. So that in that case, we will see what is the difference and what is the distance how we are calculating in the case of a rectangular isolated footing. So let's see. So to calculate the shear force at a x1 axis, so what we do, shear force as a x1 axis. So what we do, first calculate the force. What is the UDL? So UDL is Q naught into B, and then we have to be multiply with what is the length. So we will see that shear is happening. We are calculating shear at this point. So and from the left side, this length of distance of this UDL are causing this shear at this point, right? So UDL into this length. So what is this length? B minus B divided by 2 minus T. So same thing I've written here. So we'll see this distance, that is this distance, that is this, and this is the UDL that I've written here, right? So UDL into what is the length of UDL that causing the shear at x1 axis that we have calculated. So you can see after solving, we can write like this. So punching shear, there is an extra punching shear, or also we can say two-way shear. Two-way shear. This is called one-way shear. This is also called one-way shear, and this is called two-way shear. By name, you can get some idea. One way means one direction. You will see this shear is occurring. Means this is the, suppose this is the foundation. Means shear either happening in this direction or in this direction. So this is called one-way shear. Suppose this is the footing, and shear is happening from the both direction, like this and like this also. So this is called punching shear and two-way shear. You will see. Okay, so in this case, so punching shear, the critical section is taken at a d by 2 distance from the face of the wall or from the face of the column, right? That you can see. So in this figure, you will see this is the column, and this is very important. You have to be very careful, right? This is the column dimension. So d by 2 we have to go this direction, and d by 2 we have to go to this direction. So the total width will come b plus t, b d by 2 plus b plus d by 2. So it will come b plus d, right? So in this side also there is a b, because this is the square column. So it will come here also b plus t. So this portion at this position, this punching shear will come. So what is meaning of this punching shear? So what will happen? Column, this is the column. So column by this footing, it will go down. It will settle. It will go down. Respect to the other portion. Respect to the other portion. So this portion will go down. So that you will see. See, I mentioned. So don't be confused about this. So I said this portion will come at this dotted line, and this portion will come at the dotted line. So see this, except this color portion, it will be remain in the position, but this portion will go down. Means you will see that column with this footing will go down, and this at this place, at this edge and this side, you will see there is a punching shear. The shear is developed, and this portion will get. So how we can calculate? So we have to calculate what is the punching shear force. So what are the force that causing for punching shear? So we will see whatever the pressure is coming on this colored portion, that is causing for punching shear. So how we can calculate? So see. So see, what are the pressure? Pressure at the Q note. Q note pressure is acting below the bed of the footing. So Q note pressure is developed, is acting on the footing from the inner upper direction, and we have to calculate what are the force that happening due to the shear by this portion. So we have to calculate area. What will be the area for this colored portion, right? So that we can write, because this is the square of B side, and this is a square small b plus D side. So both are a square. So what we will do? We will just calculate this area. We will calculate the side of area of this, and then we can divide. We can subtract area of this. So we can get this color portion. So what we are going to do? We are going to calculate area for this, and then we are going to deduct area of this. So we will get area of this portion, right? So that we are going to do. We will see. So Q naught, what will the area of B square minus B see, at this point there is a capital B, means this is the width of the foundation, and this is the width of the column, right? You have to be very careful about this. You cannot write like capital B or small b. You can change. You cannot change, right? And this is the effective depth. Effective depth. So that same thing I have written here. Same thing I have written here. You will see. See, same thing I've written here. At this point. So now what we are going to do? So this was the punching shear force. So this is the external force that causing the punching shear on the footing. So what is the resistance of punching shear? So who will resist this punching shear? What is the material of the footing? So in this case, material of footing is reinforcement concrete. So concrete will resist the punching shear, right? So we can calculate what are the capacity to resist the punching shear. What are the strength of the concrete to resist the punching shear, right? So that we can calculate. So punching shear force, we can calculate Q, here the QHP, that is safe punching shear. Here the QS is safe punching shear. So how we can write 4 into D, so that you will see. See, in whatever the I mentioned with colored, so this portion will be go in the shear, it will go down. So whatever the rest portion will resist, so suppose slide will occur. So we can write what is the area of this, there where the slide will occur, right? So you can calculate like this. So you can see the top side. So top side, there is a width B plus D, D by 2 plus B plus D by 2. So it will be B plus D. So whatever the length perpendicular to this figure, perpendicular to this figure, and you can say the depth of the footing. So into D naught, you can see this is the area where the shear is, punching shear is happening. So this D naught is overall depth. This D naught is not effective depth. This D naught is overall depth. So we can write what will be the overall depth. It will be D plus C, where the D is the effective depth and C is the cover. It is the cover. So D plus C, in the footing you can see this is the D and this is the C. But this overall depth is called D naught. This is D naught from here to here. This is D naught, right? So we can write D naught equal to D plus C. Are you getting my point? So you can see in this case here area is B plus D into D naught. Here also perpendicular. What is the width perpendicular to this? Perpendicular to this figure, that's D naught. So here also will come B plus D into D naught. Similarly, here will come B plus D into D naught. Here will come B plus D into D naught. See, this area is you cannot see in this figure because this is the 2D diagram, and we cannot see the what is the depth perpendicular to this direction. But you have to understand there is a D naught perpendicular to this direction, and that is I've shown by here. So we can write 1, 2, 3, 4. So we can write 4 into each area. So each area is B plus D into D naught. So we have to write the area. Or either we can say also sigma SP into perimeter of punching shear, perimeter of this area. So perimeter we can write 4 into B plus T into overall depth. So somewhere you can see the formula is written like this. So I'll say punching shear into perimeter of this punching shear area, and there is a overall depth, multiplying with the overall depth. So we can write like this. So what is meaning of this? What is meaning of this two? We will see this is the force that causing the shear, punching shear, and this is the force that is resisting. So we can see it should be greater than equal to punching shear force. Means resisting force should be greater than punching shear force. That for if this is the case, then we can say this footing is safe in case of punching shear. Are you getting my point? So this is the case. You can see if the resisting force is greater than or equal to a punching shear force that is causing on the footing. So we can say this footing is safe in punching shear, right? So we can calculate by equality sign. So after calculating, we can write this. So equating both the forces, one is the causing the shear, punching shear, and one is the resisting the shear, punching shear. So we can write, and by equating this two equation, we can get the D naught, overall depth. So we can write this formula, D naught is equal to Q naught into B square minus B plus D whole square, divided by B plus 4 into B plus D into sigma SP. Okay. Are you getting my point? Okay. So now you can see there is some important points you have to be keep in mind to when we are going to design an isolated footing. So the first can for the uniform contact pressure distribution, the center of gravity of the footing should be coincide with the center of gravity of the column. This is very important to get the uniform distribution of pressure at the base of the footing. So what is the point? What what is meaning of this? Suppose this is the column and this is the footing. So center of gravity on the footing, suppose center of gravity footing is here. This is the center of gravity of footing. And center of gravity is column is there here. So this line should be coincide. It cannot be like this. It should be like this. So suppose that line of footing is in this direction, column in this direction. So we'll try. We cannot design like this. We cannot design like this. This is wrong. Suppose this is the CG for column. So we cannot design like this. You will see this is the CG of footing is here. CG of column and this is CG of footing. So this is wrong. This is wrong. So what we do, suppose this is the column and this is the footing. So this is the CG of column and this is the, we will try to coincide this. Okay, so this is good. Okay. Okay, the second is the design for the square footing for a circular column. The circular column is generally substituted by equivalent square column. See, suppose there is a square column. There is a, you can see these cross sections like this. So there is a square column. So by going to design a square footing, so what we do, we assume this circular column is a square like this. So what is we have to be what we have to do? So whatever the area of this square, it will be equal to the area of this circle. So by keeping these things in mind, we can go for the design of footing. So area of the square would be area of the cross section of square of column would be equal to the area of square of area of the circular column, right? So this is also very important. Third case, in the case of rectangular footing, the length and the width should be, so the length and the width should be so chosen that bending moment in each adjacent projection is equal to the moment of existing footing. So what we do in this case, you have seen there was a square footing. So we have worked in this direction. We will work in this direction. Both are the same thing because the same dimension. But in the case of rectangular footing, where this is the length and this is the width, right? So you will see, if you will calculate in the one direction, you have taken the UDL into L and all this calculation bending moment from here, and from D distance, all these things we have done. So that will come in a different value. But when you will analysis do in this direction, like you have done like this is the width, this is the L. You have do the analysis like B into B. So you have calculated the critical size of taken from here, right? Like for bending moment from the face of the column, critical shear for diagonal shear, D distance from the face of the column. So that will be different. So what we do, in some cases you will see whatever we have got in the length direction, that will provide in the same in both direction. But for the economical condition, what we do, we go to analysis in the both direction, once in the length direction or one in the base width direction. So we go for both analysis and we see it should be satisfied from both the sides in each adjacent projection, right? Okay, so this is very important when you are going to design rectangular footing. So now I'm going to discuss one problem, that is square reinforcement concrete footing design. So in the question it is mentioned, design a square reinforcement footing for the following data, and the data we have, you can see column load, that is by notation we can write, this is the given Q. Allowable pressure is given, that is QNA, right? And this is the size of column into B. This is the QSP is given, this is cover C, so that we can write right. So now we are going to solve. So see in the figure, width is mentioned, width of column is mentioned 0.5, that is small b, and there is a. So first, what is the procedure? First, we have to calculate the required area by dividing Q divided by QNA. So 900 divided by 210, 4.25 meters square, right? Okay, so required width we can calculate because this is the square footing. So we can calculate width by taking the square root of 4.28. So we get 2.07. So see here, we have provided some greater area, greater width compared to required width, right? So now we have to calculate what is the actual width. So we have to calculate the actual provided area. So we have provided 2.25. So area we can calculate by taking the square of this 2.25. So that we get 5.06. 5.06. So now we have to suppose you can see here we have provided some greater area as compared to required area. So we have to go for calculation to what is the actual pressure will develop at the base of the footing, right? So that we can calculate 900 divided by 5.06. It came 178 meters square. So that you can see in this figure, I provided 178. 178. So I don't think it is right. Okay. This area is came 178. So here you can see I have just mentioned UDL, right? No, not UDL. I have just mentioned this uniform pressure, whatever the pressure will develop at the base. So I have written here. This is Q node. This is not UDL. This is Q node. The actual pressure that will develop at the base. Actual pressure, right? Okay. So now we can go for next procedure. So now we can in the question it is given cover is given 50 mm. So we can calculate overall depth where the D is the effective depth. So D node we can write D node is equal to D plus 0.050. So we have converted the mm in the meter. So now you can calculate the dimension, the face of the wall column from the edge. It will come 0.875. And we have this relation we have derived in the previous slides. So it is by equating, you can get this overall depth equation by equating the punching shear force equal to the resisting shear force. So by equating both equation, we can get this overall depth, right? So in this formula, you can see already we have calculated one Q node 178 meters square. No, this won't be meter square. Sorry, this will be kilonewton per meter square. Okay, this can't be meter square, right? Don't worry, this will be in kilonewton per meter square. Right. So already we have calculated 178 kilonewton per meter square. This is the actual pressure. This is not a area, so it will be kilonewton per meter square. We have B naught, that is 2.5. We have the small b, that is 0.5. We have the effective depth. So we have effective depth that is unknown, right? So in the whole equation, you will see in the both the case, this is not meter square, kilonewton per meter square. Just correct it, okay? Okay. So in this equation, you will see there is a d is unknown, so we can calculate d, right? So you also try to solve, you will get this result. I have just calculation, I have done the calculation, so I'm writing directly, I'm writing all this value of d. So by solving d is equal to, we get 0.1877 meter. Okay, and we are assuming that we are taking 0.25. Okay, so we have provided some extra width, extra depth, effective depth to be safer side, right? So now we have to calculate the bending moment at a critical section, and that critical section is at the face of column. So on x-axis, so we have directly derived the formula. So Q naught into B minus B by whole square divided by 8. So we have all these value. By putting all these value, we can get bending moment at x-axis, that is 154 kilonewton meter. Okay, you also try to solve. If you are getting different value, so just leave some comments on the comment section. Okay, so now we will calculate critical for diagonal shear. So critical section will be at a d distance from the column, face of column. So we are going to find friction shear force at a x1 axis. So we can that is distance d. So d we have taken as option 0.25. So the x1 axis will be from the edge, that is 0.850, and we have derived all this formula. So Q naught B, small b, d we have. So by putting all these value, we can get the friction shear force, that is 350.43 kilonewton. Right? Suppose in this case, we are not going to design the reinforcement. We are not going to design the concrete. So if you will design the concrete also, we need all this information. So if we have this value bending moment, so by using this, we will take all this condition, and we will go for to fix the sigma sp, all this thing. So in the geotechnical point of view, we have to be just proportion the dimension. We have to calculate the width, length, and depth. We have to check what are the maximum or critical bending moment and shear force, and for the punching shear force, what are the different are coming. See, in this case, you can say, so we have calculated the bending moment, we have calculated the shear force. So what about the punching shear? So for the punching shear, you will see this equation we have applied, and by using this equation, we have calculated d. It means whatever the d we get, and we have provided this d, or we have provided greater than required d, that is came from here, right? So if we are doing this procedure, it means the footing will be safe in the punching shear itself, because we are using this. So what is this? The numerator is here, the forces which will cause the shear, punching shear. What is denominator? So denominator in this case, you will see by multiplying this all, you will see this is the resistance, resistant force for the punching shear, right? So by using this equation means we are very sure about we are safe in punching shear. The footing is safe in punching shear, right? Okay, so always when we are designing some foundation and we are solving some problem for the design, so always there is some steps. So what we have to do, we have to just follow these steps. Okay, so in the first case, you will see there is a step, we have to find the required area. Then we are going to find the actual pressure, and then we have the actual pressure. Then we have to find the whole dimension, that whatever the section for the bend beam movement and what is the distance from the face of the column and this all this edges. When we have to work on this critical section for the shear, we have to see the it should be safe in the punching shear. So all this procedure we have to follow. Or already we have derived all this formula in the previous slides. So that you remember, and how the formula are coming, you have to be very be careful. You have to understand each and everything. Restart, just put the value and get the result. Okay, so thank you. These are some reference that I've taken to make this lecture. So thank you. In the next lecture, I will discuss the design of isolated footing. But for eccentric load, we will see at that case where the load is not coincide with the CG of column. So how we are going to design the foundation and what things are there. We will see. I have discussed in this lecture also. The pressure will develop at the base of the footing that will not be uniform. That will be not uniform. One side you will see there is a minimum, other side there is a maximum. So that is problem. So the maximum pressure should be safe compared to the allowable soil pressure. It should be less than equal to QNA, right? So that we will see in the next lecture. So thank you.